Ahoy Captain, and welcome to How to Decarbonize Your Ship, the show in which we provide guidance on regulations and decarbonization measures. Today is going to be special because we're going to look at all the container ships in a database, plus some more, in order to analyze and determine the average shore power consumption, power demand in kilowatts, of container ships in general. Why? That's because of upcoming regulations, in particular Fuel EU, that's going to enforce the use of shore power while in port, and that means that it's critical in order to get a good estimate on the average shore power requirements for ships, especially for not just ship owners, but also port authorities, terminal operators, designers, etc. So hopefully this episode will provide you some guidance on the average shore power demand of container ships, and of course we're going to provide you with all the tools you need in order to make your own analysis. So let's have a look at what we are going to do, and let's kick off with the average. What we found is that the average shore power demand for all the container ships combined is 600 kilowatts. You might think, what? No pun intended. No, that's the average of all the ships of 4 different sources that we used, and we're going to show you exactly how we derived at this number. But if you're going to ask me what is the average shore power demand of container ship, and I have no clue about your ship, I'm going to say 600 kilowatts on average. Of course, there's a high degree of variation. It ranges from, well, actually 0 in some sources, but all the way up to 3800 kilowatts, and that's the maximum average. I'll show you everything later, because probably there's going to be post-Panamaxes or whatever, the biggest ships, container ships in the world, probably with refrigerated containers, might have some more power demand than this while moored. But this is about the lowest and the highest that you get with an average of 600 kilowatts. We looked at 4 different sources, the IMO, a DNV, and also our own database, plus EMSA. What we see is that IMO, DNV, and our own database are very similar, all ranging above and beyond 600 kilowatts, so they're very close, which gives us confidence. EMSA is a lot higher than the rest, 1500 to 3800 kilowatts, and we'll show you, of course, all the details in this video. Look at me, I'm talking all fast and enthusiastic, but before we dive in, let's first have a look at some of the disclaimers, of course, because this analysis, well, it's not exact science, it's guidance. Exact science means measuring at the ship level, which we are not doing at the moment, not just because we're using different sources in our own databases, but also that's not publicly available data. So we're looking at averages and trusting the law of big numbers. And of course, I'm going to show you all the assumptions and details that we used. It is constantly evolving. When we learn more, we're also going to improve our tools and get you better estimates and analysis. It's made by humans, so if there is an error, let us know in order to improve. And finally, like I just said, it's made with publicly available data. You can find it all for yourselves, except of course our own database, which members can use indefinitely in order to make their own analysis for their ship specifically. That's it. Enough said about disclaimers. Let's dive into the analysis. In order to get you the best estimates and making sure that we are not cutting corners, we looked at 4 different sources. Our own database, IMO, DNV, and EMSA. Our own database included 1144 ships between 5,000 and 100,000 GTs, which, as you can see with the assumptions stated here, and I'll explain them later when I'm showing you the tool, leads to an average power demand of 584 kilowatts. We do have some outliers, and that's of course the whole reason why we built the average shore power demand tool, because we want to pinpoint exactly some details of specific ships in order to make business cases for those ships specifically. Anyways, we derived 584 kilowatts, which was closely aligned with IMO and DNV, and not with EMSA. That was the only outlier of all outliers. For IMO, we took the 4th IMO greenhouse gas study that has a nice section and table on the averages of shore power demand for specific ship types. The same applies to a DNV-GL. We looked at GLOMEP, which is the global efficiency. Oh man, that's very small. Global Maritime Energy Efficiency Partnerships. They have a very nice article and some great tables on the average shore power demand of ships. And then finally, we took the shoreside electricity report, that is guidance to port authorities and administrations from EMSA. There is quite some difference in the assumptions made by these individual sources. I'll show you that when we go to those individual sections, but we looked at an individual ship level. IMO looked at the container level, so the amount of 20 feet equivalent units. DNV and EMSA looked at a GT, so vessel size, and we tried to make chocolate out of it all, but you'll see that it's somewhat hard to compare. Still, we managed as follows. In order to make it comprehensible, we took the 4 different sources on the y-axis and we plotted the lowest, average and highest power demands, or actually the averages of those, on the x-axis. And the resulting values are 549 kilowatts for IMO, about 725 kilowatts average for DNV, 3,417 for EMSA, and as you can see, about 584 kilowatts for sustainable ships. Again, if we're going to look closely at the data, you'll see discrepancies and assumptions, but this we did in order to get at least some feel of all those different assumptions, data points, etc. Our take from this is that actually, like I said, 600 kilowatts is pretty close if we don't have any information at all, and EMSA is quite high, so maybe they simply looked at different kinds of operational profiles. Hard to say, we have to dive into data deeper, but this is, at least for us, a very good estimate on the averages. So that's enough said. Let's have a look at the average shore power tool, and I'll show you all the intricacies and the details. And here we have the tool. I'm on the membership page, so this is the premium tool. If you watch this video and you can't find the exact same data, that's because we're using the premium. The premium is a bit different. We're first going to have a look at IMO, then to EMSA DNV or DNV EMSA, and finally our own database to show you where we derived everything from. So let's first just click on container only. There we go, only container ships from IMO. As you can see, we have 12 ships. Well, we call them ships, but cases. You see that the dimensions are varying. IMO uses 20 feet equivalent unit in terms of units, and you see the low, average and high according to their data. With, again, here you see what I mean with taking the averages of the low, the average and the high, which results in a certain amount, minimum and maximum. So you could argue maybe this is the maximum rated power. Well, it all of course depends on the individual ship, but this would give you a good estimate in terms of what the power demand would be if you're looking at different container-sized vessels. Then looking at DNV, we see again 12 ships or cases. They take GT as their unit for comparison, and here you see a lot less variation. It's all very much closely lumped together. And the lowest is about 100 and the highest is about 1000. In some cases it's not even varying, they just give a single number for these types of ships. So basically what this is telling you is that they simply have a look at GT and they sort of multiply the tonnage with a certain value in order to derive the power demand, and that is about it. EMSA also uses GT as a unit of measurement, but they have a few less cases, about half. And as you can see, their low, average and high demand is a lot higher than all the other ones. Not just our own, but also IMO and DNV. One final note before we move on. As you can see, all these different organizations use a generalized approach, different ship sizes, either in terms of containers, 20 feet equivalent units, or GT, gross tonnage. What we have done with sustainable ships was have a look at the individual ship level and the installed auxiliary power on board. Let's have a look. And here we have the graphical representation of our database. We have power demand in kilowatts on the y-axis and it's plotted against gross tonnage on the x-axis. And here we of course need to go all the way up to 100,000 gross tonnage in order to get all the ships that are included in this tool, about 1144. And there we derive at an average power of 584 kilowatts if we assume an auxiliary engine load of about 30%. And that's very important, of course. This coincides nicely with the other data that we have from IMO and DNV. However, it really depends on the specific ship, as you can see here. What we do is we assume a certain average engine load while it's moored in port. Typically I'd say it's between 20 and 40%, although I've seen cases where it's a lot lower. Sometimes it's higher, but generally speaking I'd say it's between 20 and 40%, hence the 30%. and it has some peaks all the way up to, let's say, depending on the operational profile, but sometimes pretty high, up to 80% or more. What also depends is the amount of engines installed, and we can also have a look at the total amount of installed auxiliary power. What we did in this analysis first was simply look at the single largest main diesel generator, that is the main auxiliary diesel generator. What you can also do is take a look at all the different auxiliary engines installed on board, as you can see here, and then we get a different picture, a lot higher. Generally speaking, I don't see a lot of vessels that have all their engines or auxiliary engines running while in port, but again, it really depends on your ship type, especially some container ships, again with a lot of refrigerated containers on board, they might actually need more power in order to power all those container units. In any case, what we can do is here take a look at your specific situation. You can even look up different engines, types, container ships, and if you download the database, you can have it at a ship specific level, so you can even find your ship entirely. One final note before we close this session is that, of course, here you see a, well, let's say pretty much linear regression. We determined it was about 10 watts per gross tonnage. I think that's a nice rule of thumb to close out with. Again, here we see a few outliers. My guess is that these are container ships that have either a diesel-electric propulsion system with a lot of auxiliary engines, or just main engines installed on board that have a special operational profile. But generally speaking, if I have to put my money on it, a general container ship terminal for, let's say, not very large post-Panamax, etc. container ships could make do with a low voltage shore power system below 1 megawatt. That, well, I can't say for sure, but I'd say that's about 80% of all the dots are below 1 megawatt. So that gives you a pretty high degree of confidence, together with the other information from IMO and DNV, that the average is about 600 kilowatts, and in this case, well, not this case, I would cap it at 1 megawatt, makes life easier, unless you want to have specific designs and very large container ships for your terminal. As always, there is so much more I want to say, but it already took me long enough in order to explain everything to you. If you want more, if you need more, we're here for you. You can sign up to the hub at Sustainable Ships in order to get all the tools, the support, and the solutions for your business case at your fingertips. Simply go to the website and sign up to download the database and use all the premium tools and features. Thanks for watching this video and have a great day.